So buffers, more chemical discussion of buffers. For most solutions, if you add some acid, what's going to happen to the pH? It's going to go up or down? It'll go down. And if you add base, like sodium hydroxide to a glass of water, what's going to happen to the pH? It's going to go up. And it's going to change significantly. Buffers resist pH changes. And buffers are solutions that contain significant amounts of a weak acid and its conjugate base, or vice versa. This is where, when you write it all out in words, it gets really long and confusing. And so I actually like this version better. So what, vice versa? Well, it could also be a weak base with the conjugate acid. Just a combination of a weak acid or base and its conjugate whatever. Okay? If you have significant amounts of both of those, then you have a buffer system. If you just have the weak acid or just the weak base, it will dissociate and form the conjugate base or conjugate acid, but it doesn't dissociate enough to be able to do much, and so it cannot really act as a buffer by itself. So you have to have both of them present. So here's an example. Acetic acid and sodium acetate is a commonly used buffer system. So here we have the weak acid, acetic acid, and here we have sodium acetate. And so we put the sodium acetate and the acetic acid in here. And let's just write out that little equation. Let's choose a color. Is that too fat? No, that's okay. So what does the acetic acid do when you put it in water? It dissociates. And we're just gonna do it the simple way. And we've got H plus C2, H2, H3O2. Right? It dissociates. It forms acetate ion, but it only forms a little bit of this. And what happens when we put sodium acetate into water? It dissociates. Does it do it partially or completely? I'm hearing partially because we've been thinking about weak acids and stuff, and we know that this is related to a weak acid. But is this compound soluble or insoluble? It dissociates completely. Sodium compounds are soluble. Acetate compounds are soluble. So this is an ionic compound, and it's going to dissociate completely. So we're going to get sodium ion and acetate ion. Now, what is the sodium going to do? Nothing. It's going to hang around. Okay, I think I've mentioned to you before that I think about solutions like this as parties, and you've got the cation and the anion, and the one's male and one's female, and they come, right? And so these get-togethers like this, you have to come as a pair. You can't come by yourself. So acetate can't show up by herself because you can't have a beaker of just negative ions. Nature doesn't like it when charges get separated, and so we can't do that. So the sodium ion is just along for the ride. It's not going to participate. It's a spectator ion. It could be potassium, could be lithium. It really wouldn't matter at all what it is. But there has to be a cation there to balance the charge on the anion. So we've got acetate ions here, and we've got a few acetate ions from the dissociation of the acid, but we also have a more significant amount of the acetic acid here. So this is going to make a buffer. What's going to happen if we throw some sodium hydroxide in here?
Can we get some H plus attachment to it, right?
So this acid could react with sodium hydroxide, right?
Yeah.
So HC2, H3, O2, plus, I'm just going to call it the hydroxide. What's going to happen when we do that?
You get water and acetic acid.
You're going to get water and acetate ion.
Not acetate
right? Everybody okay with that? So because there's acid in this solution, if we throw some base in there, the acid will neutralize it. Well, what if we throw some acid in here? What if we throw some HCl in here? The acetic acid is not going to do anything to it. But what about this guy?
Yep.
The HCl plus acetate. Acetate is the conjugate base of a weak acid. The conjugate base, it can react with the acid. So it can form acetic acid, and then the chloride's just kind of hanging out there going, what happened? So that's how a buffer works. We have, from this weak acid equilibrium, we have a significant amount of the acid and the conjugate base. And the only way you can get a significant amount of the conjugate base is by adding a salt of the conjugate base, because you won't get enough from the dissociation of the acid. Any questions? So, I don't usually do the conceptual connections, but I kind of like this one. Here's 4 different solutions. Which one of these is a buffer? Let's just look at them. They've all got 0.1 molar this and 0.1 molar something else, so the concentration's not different. Let's look at this. What is that, HNO2? It's an acid. Strong or weak? Weak acid. Okay, so that's a good sign for it being a buffer. What about this? It's a strong acid. Weak acid and strong acid. Does that make a buffer? No. How about this, HNO3? Strong acid. What's this? It's a salt. NO3, is that related to HNO3? Yeah, so this is the conjugate base, but it's a conjugate base of a strong acid. Strong acid won't work because the strong acid dissociates completely. And so you don't have any left to react with and neutralize the base. How about this one? HNO2 and NaCl. No, here we've got a weak acid, but that's not the conjugate base. How about this last one?
There we go.
Yeah. So we have the weak acid and the conjugate base. Anybody have any issues with that? So the conjugate base is an ionic compound. Just cover up the cation. Oh, that's NO2. That is different by a hydrogen ion from this guy. And that tells us that's a conjugate acid-base pair. Well, how do we calculate the pH of a buffer solution? Well, let's think about a solution initially containing 0.1 molar acetic acid and 0.1 molar sodium acetate. So we put both of them in there. And we could kind of represent that here. So we're starting with 0.100 molar that and 0.100 molar of this guy. What's going to happen? How would we solve something like this? We want to find the pH. We need to find the concentration of this guy, right? What is this initially? Essentially 0. What is the real concentration in pure water? 10 to the minus 7. But 10 to the minus 7 is so small compared to 10 to the minus 1 that it's essentially 0. Right? So if we were making an ice table, this would be our initial line, the initial concentrations. Could we, using our knowledge from the previous chapter, could we figure out what the equilibrium concentration of the hydronium ion is? Yeah, I think we could. Yeah, we're going to need the Ka. And then let's think about this. Because we have this acetate ion here, that is going to cause the weak acid to ionize even less than it normally does. right? If this was 0, then the reaction would definitely proceed to the right. Because there is already a bunch of this here, it's still going to go to the right and make some of this, but it's only going to go a little bit. So the presence of this reduces the ionization. And that's a, that's a phenomenon known as the common ion effect. Because this ion is common with the ion in the acid, it reduces the amount of ionization of the weak acid. So just thinking about this, we can predict that the hydronium ion concentration is going to be less than what we would normally expect from a 0.1 molar acetic acid solution. So the pH is going to be higher than just pure acetic acid. Okay, so let's actually do a calculation here. Here we have that sodium acetate acetic acid buffer, but now we're talking about 0.2 molar in the acetic acid, 0.1 molar in the sodium acetate, and here we have the Ka given for the acetic acid. We do need that. Ka values, if you look for them on the internet, you might find that they're sometimes reported a little differently, and it depends on the source. So just be aware of that. You could, if you didn't get your Ka from the same place as the person setting up the key, you could end up with a slightly different answer, and you may have done all the work correctly. So just be aware of that. So the way we're going to do a problem like this is we're just going to treat it as an equilibrium problem. Now, personally, I get a little tired of writing out acetate, C2H3O2, and so I prefer to just use the generic representation, HA being in equilibrium with H plus and A minus. So A minus is the conjugate base, that's the acetate ion here, and HA is the weak acid. Now I'm just going to use that as the top line of my ice table here. So it's 0.2 molar in the acetic acid, so initially we've got 0.200 molar here, and 0.1 molar in sodium acetate. And then we're going to say that the hydrogen ion concentration is essentially 0 to start with. And then the next line is we're going to figure out how is this going to change. So hopefully this is becoming fairly routine for you guys now. So here we've got 0.2, and here we've got 0.1, and this one's 0. So this can't go minus x, can't really go lower than that. So we know it's going to go to the right. So the acid is going to lose, and because of the stoichiometry, we'll call that minus x. And then this is going to be plus x and plus x. And then at equilibrium, what we've got is 0.200 minus x and 0.100 plus x. And then we set up the equilibrium expression. Ka is equal to 1.8 times 10 to the minus 5, which equals the products multiplied and divided by the reactants. And since there's no coefficients in here, we don't have anything squared or anything like that. Now, you could solve that two ways, right? You could try the x is small approximation, or you could use the solver in your calculator. Do you think the x is small approximation is going to work here?
It could.
And it's quite likely, right? So let's just go with that. And so what I'm going to do is I'm going to ignore this, and I'm going to ignore that, because x is small is saying that x is so small relative to 0.1 and 0.2 that it essentially doesn't matter when we're adding or subtracting it. So then we get Yeah, I'm writing too big. Oh, wow. So then we end up with x equals 0.2 divided by 0.1, 1.8 times 10 minus 5. (1.8 EE minus 5 divided by. So I'm coming up with x is equal to 3.6 times 10 to the minus 5. Anybody else get that number? Anybody else do it? Okay, I got an affirmative. Thank you. So, is our approximation valid? Yeah. We can look at that and see that it is, but the rigorous way is to take this number and divide it by what you're adding it to and make sure that it's 5% of this number or less, right? And it is going to be. So x equals that, but we're trying to calculate the pH. Sometimes, we get all wrapped up in finding x and then we forget, why were we finding x again? Oh, that's right, we wanted to find the pH. Well, it turns out that x is equal to the hydrogen ion concentration. So then the pH is going to be the negative log of 3.6 times 10 to the minus 5. So the pH is going to be 4.44. Any questions? This is really just an equilibrium problem. So, Henderson-Hasselbalch equation always reminds me of David Hasselbalch, but it has nothing to do with him. We can derive an equation that relates the pH of a buffer solution to the initial concentrations of the buffer components so that we don't always have to do that whole equilibrium calculation to predict what the buffer pH is. So let's see if I can remember the steps involved in doing this. So we want a relationship between pH and pKa of this acid. So let's start with this. What does Ka equal? Well, it's the H3O plus times the A minus concentration and divided by the acid concentration, right? And if we want to know the pH of this solution, which of those terms do we need to solve for so we can find the pH? We need to solve for the hydronium ion concentration. So I'm going to rearrange this equation so that I get H3O plus by itself. So H3O plus is going to equal Ka times HA over A minus. Yes? Through the magic of algebra, which I love you guys because I can do this, and you're like, oh yeah, that's fine. Some other classes, not so much. What did I do there? See, I was just bragging on you, and now you just... Okay. So I took this and I flipped it. So I put this whole side over here and the Ka over there. And then I multiplied by HA to get it out, and I divided by A minus to get rid of that. Okay? We could go through that, but it takes up a lot of space. Well, how do I get pH? Negative log, right? So I'm going to take the negative log of this side and the negative log of that side. So negative log of the hydronium ion concentration, that equals the pH. That must equal the negative log of this mess. Ka H A over A minus. Right? So here I have the log of numbers that are multiplied. That means I can take the negative log of Ka plus the negative log of the other part. This one's going to end up kind of going in circles. So negative log of Ka minus the log of HA over A minus. You okay with that? Because I have Ka times this. I don't want to split that up for my own personal reasons. I think they look nice together. What we're doing is the log of A times B equals the log of A plus the log of B. That's the algebra principle we're using. Well, what does this equal? Negative log of Ka. That's the pKa. And then what we have left is negative log of this guy. Well, negatives are nasty. Not really, but negatives can be messy. Could we change that into a plus log of something? Yeah, we can. If we invert this fraction, we can have plus log. Why do we want to do that? It's just to get rid of the negative sign. That's all. So what we're ending up with here is pH equals pKa plus the log of A minus over HA. And that is the Henderson-Hasselbalch equation. If you know the concentration of your conjugate base, the concentration of your acid, and the pKa, you can predict the pH without doing that whole equilibrium calculation. Isn't that nice? Of course, you have to remember the equation. But any questions? So here it is, typed out, using words instead of HA and A minus. So it's the log of the base over the acid plus the pKa will give us the pH. If you want to use negative and put acid over base, is that what you mean?
No, I mean like
the base is.
for the hydrogen concentration, you take the negative log of it.
Say that again.
Like this is just a shortcut instead of doing
The whole equilibrium calculation. Yeah, that's all it is. You can still do the equilibrium calculation.
Yeah, so you still do all of it.
Yeah, whatever floats your boat, right? So this is useful as long as the x is small approximation is valid. If x isn't small, this is not going to give you the correct pH. But most of the time, x is small, and so it's fine. Well, another way to kind of gauge this is just a guideline, kind of a rule of thumb. If the initial concentrations are not too small and K is fairly small, that's one way to think of it. Or if the acid and base concentrations are greater than 100 to 1,000 in there times Ka. So if Ka is 0.01 and your acid and base concentrations are 0.001, is the Henderson-Hasselbalch equation going to be okay? No, because here your acid and base concentrations are actually smaller than the Ka. It's just not going to work. So this will be useful for some people, and other people will go like, what on earth is that all about? It's just kind of a guideline to help you decide, is this small or not? So if the concentrations of your buffer are 100 to 1,000 times larger than Ka, then you're good with the Henderson-Hasselbalch equation. The equilibrium approach is always valid. And now that we've gotten so good at using the solvers on our calculators, we don't even really need the x is small approximation when we do that, right? Sometimes it's almost easier to just type it into your calculator and find the real x instead of the approximation. Yes?
So does this formula still, is it only for when you're given the concentrations of the acid and base?
Yes.
Okay, so you couldn't do it, you'd have to set up an ice table if you were only given one?
Well,
Like you can't plug 0 in for the base?
if you were only given one concentration, that would have to either be the conjugate base or the acid, and it wouldn't be a buffer solution then. Because you have to have significant amounts of both.
Okay, I see.
Yeah. It's a good question, though. Any other questions? We'll get to that. So let's do a problem. Calculate the pH of a buffer solution that's 0.250 molar in cyanic acid, hydrocyanic acid, and 0.17 molar in potassium cyanide. And we're given the Ka value. Use both the equilibrium approach and the Henderson-Hasselbalch approach.
Oh, we're doing them both.
We're doing them both.
Okay.
So kind of two things at once here. Which one do you want to do first? Do the equilibrium first. Okay. So I'm going to try to write small. We'll see if I can be successful in that. So we've got HA to H plus and A minus. And, oh, I didn't leave room for the ice. Put the ice over here. Initial for the acid is 0.250. Initial for the base is 0.170. And we're saying that the initial for the hydrogen ion is approximately 0. So then what do we do? The change. So we're going to look at this. And remember, if you predict that it's shifting in the wrong direction, the worst thing that's going to happen is your x is going to end up being a negative number. And it's okay, because when you add a negative number, you subtract, and it'll all come out right in the end anyway. So this is going to be minus x plus x plus x. So here we get 0.250 plus x. And this guy is x, and this guy is 0.170 plus x. Where?
250.
Because I had a brain fart.
Oh.
I was testing you. No, this is supposed to be minus, because, I don't know. It's supposed to be minus x. Thank you. I actually did that on my calculator. I was trying to... I like to try to work, I like to work these through before I come to class and make a fool of myself. And I actually punched them into my calculator wrong a couple times. It's like, wait a minute, that's not the right answer. Oh, okay. So then we've got Ka equals 4.9 times 10 to the minus 10. And that's going to equal the x times the 0.170 plus x divided by 0.250 minus x. Can we use x is small? Yeah. Look at these guys compared to the Ka. They're ginormous. So it's going to be fine. So we're going to pretend that we don't have that there, and we don't have that there. And we're going to solve this and find, we're going to have turn on the calculator first, that always helps. 4.9 times 10 to the minus 10. I'm going to multiply by 0.25 and divide by 0.17. I'm going to come up with x being equal to 7.2 times 10 to the minus 10. So in terms of pH, that's going to give us 9.14. Did I screw up anywhere else? Amazing. Questions? Okay, now let's do Henderson-Hasselbalch. Okay, so that equation is pH equals pKa plus log of base over acid. And that's really the hardest part in my book, is remembering which one goes on first. Which one goes on first? Who's on first, of course. Which one goes on top? So, pH equals, and they were so kind, they didn't even make us calculate pKa. It's just given to us. 9.31 plus the log of the concentration of the base, that's the conjugate base, is 0.17. And the acid was 0.250. We already established that the X's small approximation is fine, and so using this equation is fine. So I'm going to have 9.31 plus the log of 0.17 divided by 0.25, and I come up with the pH is equal to 9.14. What do you know? I got the same answer. Always good. Always a good thing. So personally, I think if you remember how to do this, that seems faster to me. Well, what if you're taking an exam and your brain freezes and you forget the equation? Well, you could either derive it or, I don't know, I haven't looked ahead that far. Or you could just do it this way. That way always works. Any questions? Yes?
For by exam, you don't mean this upcoming exam, or do you mean like next?
The next exam, because the exam this week is 14 and 15, and this is chapter 16. So this is not on the next exam. It's exam 3.
Remember this for more than 2 weeks.
KAs and KBs would always be provided, yes. Unless we give you all the other information and ask you to calculate that. But yeah, that's not something you memorize. So that was calculating the pH of a buffer solution. If you add acid or add base to a buffer solution, it will resist a pH change, but the pH will change a little bit. So we can calculate how much it does change. And the way we do that is we break this into 2 parts. We first look at a stoichiometry calculation, and here what we do is we calculate how the addition changes the relative amounts of acid and base. And after we figure that out, then we do an equilibrium calculation to calculate the pH based on those new amounts of acid and base. So we're going to do kind of a sketchy example where we don't get all the numbery, and then we'll do a real example. So the stoichiometry calculation. So the little example we're going to do here is we're going to say we have 1 liter of buffer, and it's 0.10 molar in both the acid and the conjugate base. And we want to calculate the pH after adding 0.025 moles not molarity, moles of strong acid. So the stoichiometry calculation, we're going to look at how does adding that strong acid change the HA and A- concentrations. So what we're going to do here is we're going to work with amounts in moles instead of moles per liter. Okay? And we can do that because later the volumes are going to cancel out anyway. So it's going to be okay. And it just makes dealing with things like adding 0.025 moles of acid easier to deal with. Now, when we add this, we're assuming that there's not a significant volume change that we would have to worry about. So we're going to set up a little table. Notice, this is not an ice table. If you think of it as an ice table, you're going to be confused. Because when I looked at this morning, I'm like, what? There's just dashes here? There should be X's or something. No, this is not an ice table. So we're going to look at the amounts of moles before addition of the acid. So initially, the hydrogen ion concentration is essentially 0. It's so small compared to the other things that it doesn't matter. We had 0.1 moles in that 1 liter solution of A-, and we had 0.1 moles of the weak acid. When we add 0.025 moles of strong acid, what's that going to do to these guys? It's going to change them. So 0.025 moles of acid, that's going to react with the base, right? And this is a 1-to-1 reaction. So what we're going to say is essentially that all of that acid gets eaten up by the base. So the base is going to decrease in amount. It's 0.1 minus this gives us 0.075. And over here, because of that, we're going to have more acid than we had before. This H plus that gets added reacts with the A minus. Try to think stoichiometry here, not ice table. Just really try to get away from the ice table thing.
So where's the extra 0.025 mole come from? Does it come from a reaction?
It comes from, we're adding 0.025 moles of strong acid to the buffer to see what happens.
Okay. It's under the impression it got neutralized.
It's going to get neutralized, yes. But we have to look at what's happening.
Okay.
So this is an equilibrium, right? But in this part of the calculation, we're going to pretend that it isn't.
And then use
Yeah.
that to
So when we add this in, we're going to pretend that it reacts completely just so we can get new starting values of the weak acid and conjugate base. And then we're going to do the same calculation we just learned how to do. Okay? So we're going to say, well, the buffer neutralizes added acid, so we're going to assume that it does so completely. And we're just finding our new amounts. So now we have 0.075 moles of the conjugate base and 0.125 moles of the weak acid. And we're still saying that we've got essentially 0 of the hydrogen ions. Any other questions? The table, I think, is confusing. I'm not a fan right now. So then the equilibrium part, you'll be happier about this, I think. So adding a small amount of strong acid is equivalent to changing the initial concentrations of the buffer components. That's how we're viewing this. And so what we're going to do here, now we're going to do an ice table and do a regular old calculation. These initial values now are different than what were in the buffer by itself. We figured these out. This is from that stoichiometry calculation we just looked at. So now we've got 0.125 and 0.075. And now we're going to say minus x plus x and see how it changes. So you could use Henderson-Hasselbalch, or you could do the equilibrium thing. The equilibrium thing would look like this. You'd have the x times the 0.075 plus x and divided by the 0.125 minus x. And then you could assess whether x is small, and you could simplify. We weren't given the Ka, and so we can't really follow through on this. We're just looking at the process. Oh, man, we can't get a number. We'll get a number on the next one. Any questions about this, the concept of what we're doing? So we can do we can do these calculations in moles because the volume is the same. It's all in one solution, right? The volume is the same, and so the volumes would cancel out. Let's go back to this real quick. Oh, no, that doesn't actually help very much at all. I'll just draw something down here, and hopefully it'll make sense. So Ka is equal to the, just ignore that table for now, the H plus times the A minus over the HA, right? This is equal to the number of moles of A minus divided by the volume. And this is equal to the number of moles of HA divided by the volume. And so the volumes cancel out because they're the same. And that's why we can do that. So that's talking about this bullet. If we're adding small amounts of strong base to a buffer, it's the opposite of adding an acid. So this is a little example where we're adding base. Initially the base hydroxide was 0. We're adding 0.025 moles of hydroxide now. We're going to assume that that's going to react with the HA and generate A minus. And so this goes up and that one goes down. And then you do the same calculation. So, summary, if you add a small amount of strong acid to a buffer, it converts the stoichiometric amount of the base to the conjugate acid. In other words, it creates more acid. And that should make sense. We're adding acid to this buffer. We've got more acid in there. And that will cause the pH to go down. If we're adding strong base, it's going to convert some of that weak acid to the base. It's going to form more of the base, and that will increase the pH. So just try to keep in your head which way things are going. Here's a picture. This picture starts in the middle. So here we have a buffer where we have equal concentrations of the weak acid and the conjugate base. If we add acid to this, what's going to happen? The acid reacts with the base, right? So it's going to react with the base, and so the amount of base is going to go down, the amount of acid is going to go up. And it's these changes that we're looking at in that first part, the stoichiometric calculation. Here's our buffer again. If we add base, the acid concentration goes down, and the conjugate base concentration goes up. And then we just use those new levels to calculate the equilibrium. So here's a problem with all the numbers. We need to come up with a real answer. 1 liter buffer solution. It contains 0.1 mole acetic acid. There's the Ka for acetic acid. 0.1 mole sodium acetate. So when the initial concentrations are equal, I didn't emphasize that earlier. Let's look at that real quick. Henderson-Hasselbalch equation, right? pH equals pKa plus the log of the base over the acid. What if the base is equal to the acid in concentration?
1.
It's 1. What's the log of 1? 0. So then the pH is the pKa plus 0. It's just a pKa. So anytime you have equal concentrations of the weak acid and the conjugate base, you know what the pH is. So that's kind of cool. Now I have to erase all that. Come on. because I need to write other stuff there. So we have a buffer solution, and we're trying to calculate the pH after we add some sodium hydroxide. So 2 steps. Stoichiometry first, then equilibrium calculation. Well, what reaction is going to happen when we add hydroxide? It's going to react with the acid, right? And again, I'm tired of writing acetate, so I'm just using A. And that's going to make water and A minus. So we're going to look at the initial amounts and then adding in the hydroxide and seeing how those things change. So initially we had no hydroxide and we had 0.1 moles of the HA, and we had 0.1 mole of the A minus. Okay? And now we're adding in 0.015 moles of that, and nothing of the other two. What we're going to assume is that the buffer is going to chew all of this up. It's going to react completely and go over here. And so it's got 0.015 moles of this, and so it's going to need 0.015 moles of that to react with. So that's 0.085, right? And this will be 0 again. And then this is, over here, this is going to be 0.1 plus this. So 0.115. Everybody okay with that? In the stoichiometry part, we're pretending that this is not an equilibrium. Maybe I should erase that. We're pretending that that goes to completion, because it makes everything easier. So now these are the numbers we need for our initial concentrations in the ice table. So I wrote way too big. There's multiple ways to handle this. This is one of my favorites.
Can't we just use the
Hasselhoff.
equation from here? Can't we take the added amount of sodium hydroxide, add it to
Yes, we
the
can.
base, and then subtract it from the acid, and then just plug that into the equation?
We can use the David Hasselhoff equation. Henderson-Hasselbalch. So this is the concentration of acid, and this is, or the amount, the moles. This is the moles of base. So we do have to be careful and look, okay, so this is the smallest one. Is this at least 100 times bigger than, I can't see what I'm pointing at, than this? That's 8 times 10 to the minus 2 and 1.8 times 10 to the minus 5. It's at least 100 times larger. So it'll probably be okay. So then, if we're going to do the Henderson-Hasselbalch version, we're going to do pH is going to equal pKa plus log of the base over the acid. Now, these are in moles. We can leave them in moles, though, because their volumes are the same, and their volumes would cancel out in the equation.
1 liter.
And it's 1 liter anyway. So up here, the pKa is 4.74 plus the log of the base, 0.115, over the acid, 0.085. So 4.74 0.74 plus log of 0.115 divided by 0.085. 4.87. pH equals 4.87. Did that change in the correct direction?
Yes.
It did. We added base to the buffer. We expect the pH to go up when we add base. It didn't change very much. We don't expect it to change a lot. You know, if we ended up with 13 or something, well, that wouldn't have been a buffer solution. Any questions? You could also take these numbers here and do an equilibrium calculation. I don't want to do it right now. No questions? Oh, look at the time. So we've been talking about buffers that have a weak acid with the conjugate base, but you can also have a buffer that has a weak base and a conjugate acid. So you could have something like ammonia and ammonium chloride. This is a weak base, and ammonium is the conjugate acid. These calculations are going to be similar, but when we use that Henderson-Hasselbalch equation, we need the Ka. And that's what someone was asking about earlier. It has to be the Ka. It can't be the Kb. And what do you get when you're dealing with weak bases? They tell you what the Kb is. Well, we can figure it out. pKa plus pKb is equal to 14. So you can, if you're given Kb, you can find the pKa that way. So we're not going to, I don't think we're going to do an example of that. Here's just a picture of what happens with a weak base conjugate acid buffer. Here you've got the ammonia and the ammonium chloride, and you end up with ammonia and ammonium in the same solution in relatively large concentrations. And so then the ammonia would react with added acid, the ammonium would react with added base, and it'll neutralize either one. Oh, there is a calculation. Using the Henderson-Hasselbalch equation, calculate the pH of a buffer solution composed of a weak base and its conjugate acid. Okay, so let's see if we can do this one a little faster. So we're adding sodium hydroxide. Okay, so we've got OH minus, and our buffer is ammonia and ammonium chloride. Which of those is going to react with the hydroxide? The ammonium chloride. And it's the ammonium part that's important, right?
Yeah.
So those guys are going to react, and they're going to form water and ammonia. Okay? Oh, look, I'm writing huge again. Oh, well. So let's put in what we initially have. 0, ammonium 0.2. Now, here we were given concentrations, 0.2 molar. We want to do this in moles because we're adding moles. When it's 1 liter, you could do it in molarity and it would turn out okay. But if this was 2 liters, you'd be screwed. So let's just remember, this is 0.2 moles per liter, but there's 1 liter, so we have a total of 0.20 moles. And then I was looking at the wrong number. Okay, 0.50 moles of this. And then we're throwing in solid sodium hydroxide. That's going to be hot and smelly. And then we want to figure out what are the new amounts. We're pretending that this goes to completion. So if we have 0.01 of this, it's going to react with 0.01 of that. And so we're going to get 0.019, right? Moles of that. And we're going to end up with 0.019 0.51 moles of this. Everybody okay with that? That was messy. It's a little better. And then we're saying there's 0 of this. So we need to look at these and see, are they large relative to Ka? Well, we weren't given Ka, were we? We were given Kb. We need to find Ka. pKa equals 14 minus 4.75. 9.25. So Ka is 10 to the minus 9.25. This is plenty big, right? So we can use the Henderson-Hasselbalch equation. So pH equals pKa, I don't know where that came from, log of base over acid. So we've got 9.25 plus the log of the base, 0.51 over the acid, 0.19. .68. Did it change in the correct direction? We added sodium hydroxide. We expect the pH to go up. Do we know what the original pH was? Not exactly, do we? Because these concentrations are not the same. Could we calculate the original pH? Sure we could. Be 9.25 plus the log of 0.5 over 0.2. 9.64. 9.65. So it did go in the right direction. Just a tiny bit. Any questions?